Based on the magnetic properties of some substances, they may be grouped into either paramagnetism or either by diamagnetism or ferromagnetism or ferromagnetic substances based on their properties or the qualities they possess or the features they possess. In other words, they may be grouped under di or para or ferro. Now we are going to delve a little bit much deeper into what para itself is, what di, and what ferromagnetism. So you quickly and humbly pay attention. I think the first one I'm going to consider is the ferromagnetism. Now, normally when we talk of ferromagnetism, I think this one is should I say, the strongest magnetic substance. They have strong magnetic properties. However, we can see that it even takes a longer time for it to lose its magnetism. Now, and it is as a result that the atoms, atoms of that substances definitely will contain particles of electricity, and these particles of electricity, we call them the electrons. And you and I, we know that electrons orbit around the central nucleus, and these electrons behave like an electric current in a single thin of a wire, and so it creates a magnetic field. And so this in that ferromagnetic substances, the electrons orbit around the nucleus, and as they orbit, they create or they generate that electric current, and it's like they generate electric current, and that electric current creates that magnetic field. And more importantly, the electrons are so spinning like tops, and this adds further magnetism to the atom. So because of the way they spin, they add more magnetism to the atom. And this every substance, every material that
atom, and this
every material that falls under this are called ferromagnetic substance, and they have strong magnetic properties. They have their, what do you call it, their domains well aligned, and when they get magnetized, they hardly lose their magnetism. It takes a longer time to lose their magnetism. And a typical example is they have strong magnetism as compared to the di and the para. They are way off or far stronger than these magnetic substances. And that's what we call ferromagnetism or ferromagnetic substances. These substances are strongly magnetized in an external magnetic field. They are strongly magnetized in an external magnetic field, and in the same direction and they move in the same direction as the applied external magnetic field, and it retains or they maintain their magnetic moment even after the removal of the external field. So these substances are called ferro. So even after you put them into the magnetic field, and after removing the magnetic field, they still maintain or they still retain their acquired or their induced magnetic properties. They have a very strong tendency to move from weaker to stronger parts of the external field. And the magnetism exhibited by this substance is called the ferromagnetism. And so the magnetism exhibited by this substance is called the ferromagnetism. And as a result, every material or every substance that comes under this category is termed as ferromagnetic substances. They have strong magnetic substances, magnetic properties, just as I've already said. And and they hardly lose their magnetic properties. They hardly lose their magnetic properties, and as I've said that, and they have the tendency to move from weaker to stronger parts of the external field. And so that is this. A typical example is what do you call it, the iron and the cobalt, iron, cobalt, and nickel. They are strong magnetic substances, and they exhibit that ferromagnetism characteristic or character. And so that is it. These are examples of this. So we said the ferro. So one thing we can talk about the ferro is that ferro. So we said based on the magnetic properties or based on the nature of magnetism, type they exhibit, they may be grouped under either ferromagnetic or diamagnetic or paramagnetism. And so here we are talking about ferromagnetism. Ferromagnetism. And we say that these substances that fall under ferromagnetism have a strong tendency, strong tendency to retain a lot of magnetism even after an external, after the removal of an external magnetic field. And so that is, and we said that they are very strong. They are strongly magnetized. You know, they are strongly magnetized. Strongly magnetized. We said this. I've also said that they normally align themselves in the same direction as the external applied field. They normally align themselves. So when immediately I talk about the alignment, we are talking about the domains of the magnets or the magnetic substance. So they align themselves in the direction or in the same direction as the external applied field. The same direction as the external applied field. They align themselves in the same direction of the external applied field. So, and they have ordered alignment of what do you call it? Their magnetic domains. In the order that I taught you how the domains are aligned. I spoke to you about it. So that is it. So their nature will be something like this. Their nature will be something like this. And so their nature may be something like this. No. So their nature. Yeah. That's not a sound I want to use. So they align this thing in an ordered manner. So if they were to be this thing, so these are the ones I'm drawing are the domains of the magnets. So the domains of the magnets are aligned and they move in the same direction as the externally applied magnetic field. And I told you the examples of these ferromagnetic substances are nickel, iron, cobalt. So ions get magnetized and it takes a longer time for them to lose their magnetism. So it should be straight because I'm using it. So that is it. They have well aligned electromagnetic properties or well aligned domains. Let me put it that way. Now from there we look at diamagnetic substances. And these substances are normally weakly magnetized when placed in an external magnetic field. They are normally weakly magnetized when placed in an external magnetic field. And so these substances are weakly magnetized. So in that case, we are saying that it's almost like the vice versa of ferromagnetism. They are weakly magnetized when placed in an external field. And they also move in the direction opposite to the applied field. They move in the direction opposite to the applied field. So they move in the direction opposite to the applied field. So they are almost opposite to that of the ferromagnetic substances. And the magnetism exhibited by this substance is called diamagnetism. The magnetism exhibited by these substances is normally called diamagnetism. And so every substance that falls under these exhibition of this magnetic property or this magnetic type is termed as diamagnetic substances. An example or typical examples of these diamagnetic substances are copper, gold, antimony, silver, lead, silicon, mercury, water, air, hydrogen, nitrogen. And so just as I did for this, let me also try and do same for this. So we said that this one is diamagnetism or diamagnetic substances. Diamagnetic substances. And now we are saying that they are weakly magnetized. Magnetized. And we are also saying that they normally so they are weakly. When we say they are weakly magnetized, we are trying to say that when they are placed in an external magnetic field, they are weakly magnetized, and they move in the direction opposite to the applied field. They move in the direction. They move in the that means the domains move in the direction opposite to in the direction, or in other words, you can say their domains are aligned in the direction opposite to the applied field. Direction opposite to the applied channel field. And we are looking at typical example of these are, we said we have the copper, we have the gold, we have the antimony. Then we have the water is one example. We have mercury. We have mercury. We have silicon. That's number 14. We have lead. Pb. We have hydrogen. So these are examples of diamagnetic substances, and that is it. So these are arrows. The other one, you just have to this thing. They move in the direction opposite to that of the externally applied magnetic field. And from there, we are going to look at the last one, which we call the diamagnetism. 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 Any question? So diamagnetism. Hey, we are looking at sorry. Paramagnetism. Now, with the para 2, they are weakly magnetized. They are weakly magnetized when placed. Weakly magnetized when placed in an external field, when placed in a magnetic field, externally magnetic field. Let me put it that way. Weakly magnetized. Weakly magnetized when placed in magnetic field, and they move in the same this one, they are in the same direction as the applied magnetic field. The same direction as the applied. And they normally tend to move from weaker to stronger part of the field. The magnetism exhibited by this substance is called paramagnetism. The magnetism exhibited by a substance that falls under this is what we call the paramagnetism. And normally they have their destiny arranged disorderly, or they are arranged heteroscedrically. They are arranged randomly. Let me put it that way. In other words, they are arranged randomly. And examples of these materials are aluminum. We have the platinum. We have the manganese. We have the chromium. We have the chromium. We have the sodium. We have the calcium. We have lithium. So you realize that the mium are inside part, the mium. We have the niobium. We have the niobium, and so on and so. We have copper chloride. We have the crown glass, oxygen, and so on and so forth. These are all material that falls under paramagnetism. And normally they have unbalanced electrons. They have unbalanced electrons. That is it. So in the absence of an external magnetic field, these molecular magnets are arranged at random. So in the absence of magnetic field, the molecules, or in other words, the domains, just as I'll say it, are aligned, or they are arranged at random, and that gives no resultant magnetic effects to the material as a whole. But normally, if they are placed in the magnetic field, the molecular magnet becomes partially aligned. So when they are placed in the magnetic field, the molecules now become partially aligned, with that increasing its strength. So when they become partially aligned, that increases a little, or that gives the electromagnetism in it, and that electromagnetic effect that it gains is what we term as the paramagnetism. The same for the diamagnetism. The electromagnetism these materials gain is what we term as the diamagnetism. But with the ferro, they gain a lot of magnetism because they are strong magnets, and so they are also called ferromagnetism. And examples of these ferromagnets, I said iron, cobalt, nickel. These are one or two examples under ferromagnetism, or these are few examples that exhibit ferromagnetism. Is there any question? Are there any questions? Any questions? Are there any questions? Are there any questions? Harriet, any question? Harriet, any question?
No, I'm okay.
Okay. Bridget, any question?
Sir, please no.
Guys, say please no. So, Millie, darling. So we are going to do something called hysteresis. Hysteresis. I'm going to do hysteresis. How many of us have heard the name hysteresis before? Hysteresis. Last week I told you you will be learning hysteresis. So I expect that at least you have little knowledge under it, or about it. I expect you have little knowledge about it. Patience, Ofoy. Patience. Patience. Now, at examination, you may be asked to give differences between diamagnetism or diamagnetic substance and paramagnetic substance. You may also be given, or you may also be asked that give a difference between ferro and diamagnetic substances. So you should be able to do all these things. And I'm giving you this assignment. Go and write the difference between ferromagnetic substance and paramagnetic substance. Write 4. And when you finish, write 424. Ferromagnetic substance and diamagnetic substance. So you first write for ferromagnetic substance and paramagnetic substance. When you finish, you write for ferro and diamagnetic substance. You do that for me. Then when you finish, you write the last one to diamagnetic substance and para. So let me reiterate what I said. You first write for ferro and para. Ferro and para. Those that when I give assignment, they don't do it. Ferro and para. Then you write para and di. Or let me say ferro and di. When you finish, you come and write para and die. So you go and do this. This is your assignment. Let me push it here. Right after the class, you put it on the platform, or you PM and give it to me. I'll go through. So we are going to talk about hysteresis. Please let's pay attention to this segment or this part. Now, when we talk of hysteresis, it is normally well known in the ferromagnetic materials. The ferromagnetic materials normally exhibit this principle of hysteresis, and it's I'm just going to explain how it comes about and basically what hysteresis is about and so on and so forth. Now you realize that when an external magnetic field is applied to a ferromagnet, we know that ferromagnets are strong magnets. The atomic dipoles, or in other words, the atomic molecules, normally align themselves with the external field that I've already told you about. Now, when the external field is removed, still there's part of an alignment, or there's that portion or that part of alignment that will still be retained, and the material still becomes magnetized. And so we are saying that when you place a ferromagnet into what do you call it, a magnetic field, or when you apply an external magnetic field to a ferromagnet, you bear with me that what we'll first do is that the dipoles, the atomic dipoles, or in other words, the atomic molecules or the domains will align itself in such a way to be in alignment with that of the external magnetic field. Now, even after removal of the external magnetic field, you realize that part of the alignment will still be retained, and as a result, it will contribute to the material still having been magnetized, or it will contribute to the magnet not losing its magnetic properties. Now, many physical systems naturally exhibit hysteresis. For instance, when you have a piece of iron and it is brought into a magnetic field, it retains a magnetization or magnetization. Even when the external magnetic field is removed. This I've taught you when I was teaching you the magnetization of a magnetic material. Once they are magnetized, the iron will stay magnetized indefinitely. Now, to demagnetize the iron, it will be necessary to apply the magnetic field in the opposite direction. That is where, for instance, when we want to magnetize an iron, the other day I told you that you because you want to align it, you pass it through the electrical method. That is when we are using the electrical method to magnetize an iron. Now, it is connected to a DC current, and you know what a DC current is, the current which moves in one direction. Now, when you want to demagnetize it, you reverse the reaction by, instead of applying the DC, you now apply alternating current. That will alternate the current that is already or the magnetism that is already exhibited in the, what do you call it, magnetism, thereby disaligning the what do you call it, the molecules or the atomic dipoles in the material, making the material lose its magnetic properties. Now, to demagnetize that, it will be necessary to apply the magnetic field in the opposite direction. This is the effect that provides the element of memory in a hard disk drive. Now, the relationship between the magnetic field strength and the magnetic flux density is not linear in such materials. The relationship between this magnetic field and the magnetic flux density, I've already explained what magnetic field and magnetic flux density is in our previous class. It's not linear in such material. Now, when you want to plot the relationship between the two, we are going to get increasing levels of the field strength, and it will further follow up with a curve at the point, and so on and so forth. Now, you realize that it will get to a point whereby it cannot be magnetized again, no matter the amount of external magnetic force or magnetic field you apply on it, it will still remain the same. That is what the other day I told that what happens that we say that magnetic saturation has been achieved. Magnetic saturation has been achieved. It is saturated. Amen. In other words, amen, or it is satisfied. So if you add more food to it, it won't even affect it. You just keep adding. Now, in other words, too, when you also want to remove or demagnetize it, you can also demagnetize to a certain point where you also get saturated, but in the opposite direction. That means, and also it has gotten to a point whereby anything you do to it, it won't have any effect to it. You can hit it, do it anything, because you've already taken away the magnetism in it. So no matter what you do, it's also magnetically saturated in the opposite direction. Now, if the magnetic field is now reduced linearly, the plot relationship will follow a different curve. And so when it is increasing, it will follow an upward curve. Now, when it is decreasing, it will follow a different curve. Follow a different curve, and we are going to talk about that. And that relationship between the magnetic strength and the magnetic flux density is normally what we call the X-shaped loop. And I'm going to draw it, and I'm going to teach you how it is done, and so on and so forth. And that loop, we call it the hysteresis loop, magnetic properties. And I'm going to explain everything. So that anywhere you see an hysteresis curve or something, you should be able to understand how it works and so on and so forth. So I've already given you the basics, talking about a ferromagnet and magnetizing a ferromagnet. And when it gets to magnetic saturation, there wouldn't be no addition of this and so on and so forth. And you can also demagnetize for it to also get saturated, but in the opposite direction. We are going to talk about that. And in this diagram, I'm going to use what they call, I'm going to draw a Cartesian plane. And that we will use to this thing. So we are going to draw a Cartesian plane. So so we can let's say this is our Cartesian plane. Now, when you look at the Cartesian plane, you bear with me that normally this side is the positive y. This corresponds to positive y values. This side, or let me put it this side, the first quadrant are normally positive, all positive. Then you are going to get positive and negative here. You are going to get negative, negative. You are going to get negative, positive here. And so that is it. So this side and this side are opposite. This side and this side are opposite. So I'm going to get something like this. And so in a typical hysteresis loop, we are saying that if you have a material, so you will bear with me that here is 0, here is 0, 0. And when you have a material, and the y curve or the y distance, the y axis or vertex, we call it the flux density. This we are plotting the curve of flux density against that of magnetic force or magnetic strength. And so the x what do you call it, vectors or x line or axis is what we term the magnetic force, and this y will be our flux density. And I've explained what flux density is. So here will be our FD, flux density. In other words, you can decide to name this part B, where the B is our flux density, and we can magnetic field is denoted by H, or magnetic strength, the strength of the magnet is denoted by H. You bear with me that at this point, the magnet would have no, or the magnetic material has no, what do you call it, a 0. Here and here, yeah, 0. Then that means we are saying that if this is at the origin, the material is at the origin, then we are saying that it has no magnetism in it, but it's a magnetic material, or it's a ferromagnet. Now, when we add more magnetic strength, there's the magnetic field. When we keep adding magnetic field, let's say here is, we can name here F. Oh, the F, this F you can see is the applied magnetic field. So now when we applied magnetic field here, it is just expected that the magnetic strength of the distance is going to grow. The magnetic field of the material is going to grow, or is going to increase. Now when it increase, it will definitely get to a certain point. Maybe let's name this point maybe A. And when it gets to this point, let's say it is, then we say that it is magnetically saturated. That means if you apply any more what do you call it, any more magnetic, or when you apply any more external magnetic field, it won't have any effect on it. Now when we get to this point and we decide to demagnetize it, then it wouldn't pass through the same curve, it will pass through another curve. because it will need another force to get it back to square zero. And so now going to get, that's how the curve look like. So we are going to get a certain, when you get here, you can name here maybe R. You can name here R. It will come and pass through here. Here, you can also name here C. You explain all the points. Then from there, it can come to the negative R and come and be zero. Now, when we want to join this line to the side because we are talking, there's a loop. This can be our point. D. So now let me explain. So this is the path we believe there is something. There's a curve. So this you'll be seeing it in some of your textbooks. Now let me explain. So we have the ferromagnet here. We applied an external force. It's magnetism, it's magnetic strength. You bear with me that looking at this, if we were to use with a normal graph, this means that the strength of the magnetic field increase with increase in what do you call it? The magnetic field density. So, or the magnetic density increase with increase in magnetic field, whichever way. They are here. They are what do you call it? They are proportional. So there's an increment. Now, when we decide to decrease it, then definitely it also decrease with decreasing in magnetic strength. That means if you are taking away the magnetic strength, and when we take the magnetic strength, then that means the more we take away the magnetic strength, then that means the magnetic strength is hitting the negatives. And so when it gets to this positive, at this point, let's put here small b. At this point, we call this point retentivity. Now, when it gets to this point, we call it retentivity because
spell retentivity or what?
Retentivity. There's supposed to be en. So let me spell it again. There's the spellings.
Okay.
TV. There's it. Retentivity. So you humbly. There's it. Now, when we say retentivity, just as I already explained, I said that when you have a ferromagnet, because of the properties of the ferromagnet, even after taking away the external magnetic property, it will still get demagnetized. I told you that. Sorry. Even because of the properties of a ferromagnet, after even still taking away the external distance, you will still get some magnetism in it. I remember I told you that you still get some magnetism in it. And so that when it gets to this point, we are seeing that still we are reducing it. We've taken away the magnetic what do you call the external magnetic field, but you can still see that we still have some positives here, and this positive is the amount of, or in other words, is the residual magnetic properties. That means the retained magnetic properties in the magnets even after the removal of the external magnetic field. And so when it gets to this point, we are seeing that the retentivity field is